So, well, good morning and welcome to the last seminar of the year. Today we have Arianna Cortesi. She's a grad student right now. She did her undergrad in Bologna, and her undergrad thesis was about cosmology. And now she's currently a grad student in Nottingham, where she studies planetary nebula motions observed in spiral galaxies as mass tracers of the galaxy stellar population in order to recover the galaxy evolution history. Her thesis advisor is Merrifield. And now she's currently spending 1 year in ESO working with Magda and Arnaldi. So, Arianna?
Okay, good. Today I will tell you about my PhD project that mainly on lenticular galaxies, and in particular about the first of these galaxies that we have been studying, that NGC102. And this is the people with who I'm working now, that are in the Planetary Nebula Spectrograph group. My supervisor is Michael Merrifield, that's in Nottingham, but now I'm in ESO with, working with Magda Arnaldi. And, okay, I will first introduce the instrument that we are using, that's the Planetary Nebula Spectrograph, and then I will go through the main subject of my thesis, that exactly the sample of S0 that we have selected in order to study their evolutionary history depending on the environment. And then the first result we had on 1023 that were kind of particular in respect of what we thought. And so the new method we apply to this data. And finally, we'll try to convince you that what we are seeing is a merger between of two galaxies. Okay. We observe planetary nebulae because they are easy to detect since they strongly emit in two narrow bands that are H alpha, that's the red. Okay. That this red part of this is the planetary nebula, it's Cat-Eye nebula, and the red light comes from the H-alpha emission, while the green light comes from the O3 emission. And planetary nebula are a post-main sequence star with a low mass, lower than 8 solar mass. And the good thing about them is that they are not specially resolved beyond the Milky Way, so they look point-like when we observe them. Okay. And also, planetary nebulae have been studied a lot during years, and has been proved that they are standard candle in this work from Ciardullo in the 89. So they are used to determine the galaxy distance accurately, because their luminosity function is independent from the environment, from the galaxy in which is recovered, and has been calibrated on Andromeda with the absolute value of M, here the cutoff, of minus 4.48. And for our purpose, this is really good, since it gives us the opportunity of determining how many planetary nebulae we expect inside a certain fraction of the effective radius. And so we can both know how many hours we need to observe a galaxy in order to have a good number of planetary, and also if the sample of planetary we have found is complete. For this reason, okay, the Planetary Nebula Spectrograph has been built. That is this instrument you can see here, and has been built with the purpose of observing planetary nebulae. So here you can see there are 3 arms on this instrument. This is Lodovico Coccato, that's also an astronomer working in the team. So the red one here, that you can barely see, is the H-alpha camera. That's just an imaging detector, while the two arms here are the spectrograph that you can see here in detail. What happened is that the light comes in and then is split in two in these two arms. And in each one of the arms, there is a grating that disperses, that's rotated of 180 degrees, one arm respect to the other. So as a consequence, the light is dispersed in opposite directions. And here you can see a continuum that is a light from a star that is dispersed in opposite direction, but is difficult to see it when you look to the spectral image, while the planetary nebula look point-like, because we have a narrow O3 filter that can be tuned depending on the systemic velocity of the galaxy. And so, since planetary nebulae emit only in O3, if you exclude the H-alpha, they look point-like. And I've put two images of 1023. I hope you can see them a bit. And what you can see here is that the stars are this kind of trail, probably you can see this better, while planetary are this dot in here. I have highlighted only 3 of them, but there are a lot of them. And so when you move from left to right image, the star trail is fixed, while the planetary jump around. And in this way, in only one observation, we can determine the position of the planetary nebulae, that is in the middle between the two positions, left and right, and the velocity of the planetary nebulae that's given by the shift. And with the H-alpha camera, the aim is to have a more constrained determination of the position of the planetary, since here we have to fit the position of the planetary between the values left and right, while in the H-alpha we will have the exact position, and this will decrease the error on the velocity measurement. And also it will be a cross-check to see if we see the planetary both in the H-alpha and in the O3 filter, since it's possible that these dots are also not planetary nebulae, but far distant Lyman alpha galaxy or other background objects. Okay, so here I put the Hubble tuning fork, so with elliptical galaxy on the left, spiral on the right, and a zero galaxy in the apex of the tuning fork. And these are work that has been done by PNS team. There are so PNS is mainly an early type galaxy detector. So a lot of work has been done on kinematic of early type galaxy. This here I put just the last two papers from PNS. This is from Coccato et al. In 2009. And also a lot of work has been done to recover the dark matter content in an early type galaxy. And this work is from Napolitano et al. 2009. But in the same time, especially in Nottingham, the planetary nebula spectrograph has been used to detect planetary nebulae in spiral galaxy. So there is this work from Merritt et al. Of 2006 that was her PhD thesis, and was on planetary nebulae in M31. And a work will soon come out for NGC101, that's a spiral galaxy in which the planetary nebulae have been used to determine the kinematic of the thick disk compared to the thin disk, to see if they were contra-rotating. Okay, and this is my work on a zero galaxy. And the aim of this work is to determine which was the origin. Here I put spiral galaxies at M31. This is NGC1023, a lenticular galaxy, and this is an elliptical galaxy, NGC4779. And there are two main scenarios for a zero formation. A possibility is that a zero were spiral galaxies that have lost their feature and the star formation due to interaction or in the cluster or in group environment. Another possibility is that while elliptical galaxies are the result of a major merger, lenticular galaxies are the result of a minor merger, and this possibility has been studied in a simulation by Bornau et al. In the 2005, where they show that with a minor merger you can recreate a galaxy that is disky. So when you look to the isotopes, they are disky, but the kinematic is typical of an early type system. And here you can see in a merger of a ratio 7:1, and this is the merger of 4.5:1 ratio, the rotation velocity of the galaxy and the dispersion velocity inside the galaxy are, if you look to the ratio, is equal to 1 or lower than 1. While in the spiral galaxy that is used as a control sample, the rotation velocity is higher than the dispersion at all radii. And here I put some results from planetary nebula data on M31. That's a spiral galaxy, and in fact you can see that the rotation velocity in the outer part of the galaxy is higher than the dispersion. And there are error bars on this plot, but they are really little because LMR in her thesis detected more than 3,000 planetary nebulae, and for this reason the curve is really well determined. And this is a kinematic of an elliptical galaxy. You can see that the dispersion, that the rotation velocity is around 0 at all radii, while the dispersion is higher. So you have a ratio of B on sigma that is lower than 1. Okay. And then another question that is possible to ask about a zero is where did they form? There are a first study about it was from Glasser in the 97, and here I plot the fraction of a zero with respect to elliptical against redshift, and it's possible to see that the fraction of a zero decreases with redshift, while the fraction of spiral increases with redshift. So it has been thought that the cluster environment is one of the best places where you can build a zero if you want, because the cluster potential is really high and the dispersion velocity of the galaxy in cluster is really high. And so it's possible that the spiral that fall into a cluster lose its star formation and its gas with interaction with the intercluster hot medium or with the cluster potential. But subsequently, Willman in 2009 showed that this relationship between fraction of a zero and redshift can be found also in groups. Here you can see the fraction of elliptical with redshift in group that is almost constant, while the fraction of a zero decreases with redshift and the fraction of spiral increase. And a group environment is somehow better for merger between galaxies, since the dispersion of velocity of star inside the galaxy is the same, as around the same value of the dispersion of the galaxy itself inside the group. So it has, and also if you think to a hierarchical cosmological model, all cluster has been grouped in the past. And also the fact itself that we find a zero galaxy inside groups means that somehow they must form also groups. For these reasons, we have decided to serve this sample of a zero galaxy. And, well, some of them have already been fully observed, others need still time. And here we have 3115 and 7457 that are a lone galaxy. 3115 has some H1 companions, but they are not visible in optic. While here we have three galaxies that are that belongs to small groups from 3 to 5 companions. This is 1023. These two galaxies are alone, but they are in nearby, so it will be interesting to see if there is a relation between them. And these two galaxies finally are in a rich group environment with 20-30 companions. And these two as zero instead are for another kind of project because they are face-on galaxy with a bar, so it will be interesting to see if there is some relationship between them. Okay, so this is the galaxy I've been studying until now, NGC 1023. This is the group in which this galaxy is the brightest, and is a group made of spiral galaxy, apart from this S0, 1023. This is 891, just for curiosity. And this group has a very low velocity dispersion, around 52 kilometers per second. Okay, and 1023, by the way, is in the center of the group, as you will expect for an early type galaxy. Okay, and this is a picture of 1023 that was observed in the Atlas of Peculiar Galaxy, because as you can see here, is ongoing a minor merger, and so these are stars, but this here is a little companion. And so you can see that the isophoton shape of this galaxy is quite particular, so they observed it. And this is the H1 distribution that, as you can see, here is the optical, if we could see it, the optical galaxy is here, and this is the H1 that's really complex, has been studied in detail by Sanchez et al. In the 84. And here you can see that they found three main components: a tail, a red clump, and a blue clump here. And the idea is that there is a continuation in velocity between the blue clump to the tail. And the red clump coincides, this one is the small companion, this clump here. And the blue clump is in the same plane as the galaxy, while the red clump is inclined with respect to the plane of the galaxy in a kind of continuation between the galaxy inclination and the tail inclination. So what they say is that this small companion has lost almost the 90% of its H1 continent during the merger. Okay. What we do with planetary nebulae is study the stellar kinematic, and basically what we can see when we observe a galaxy, when we observe stars in faraway galaxy, is the radial velocity that depends on the inclination of the galaxy with respect to the line of sight and the azimuthal angle that we can obtain in the plane of the galaxy for each star. So, but also stars in galaxy have random motion that have a sinusoidal behavior. So if we assume a cylindric coordinate system, we can divide the line of sight random motion in the radial direction, the azimuthal direction in the plane of the galaxy, and the high. And here you can see that when the velocity is at a maximum, so along the major axis, we see sigma phi, so the dispersion on the azimuthal direction, while where the velocity is at the minimum, so is equal 0, basically on the minor axis, we can see sigma r, so the dispersion on the radial direction. I'm not taking in consideration sigma z because these galaxies are head-on, and so we don't really see sigma z, but instead visible when galaxies are face-on. And I'm sorry that... Okay, first result on 1023. This is the planetary nebula that has been found by Noordermeer. And you can see that they are rotating, so they are blue here and red here. And here are the planetary nebulae associated with the small companion. And he used the discrete tilt ring analysis to recover the rotation velocity and the dispersion. And he imposed a physical approximation that if you assume that the velocity is constant with radio, he imposed that sigma r and sigma phi are in a fixed relationship, as you can see here. Sigma r is the red dots, and sigma phi are the blue dots, and you can see they are in the constant ratio because of this imposition. And what he found is that the rotation velocity increases in the inner part of the galaxy, but then decrease in the outer part, while the dispersion is low in the inner part and increase in the outer part. And this is a kind of mixed scenario between the one I explained before, because we will expect all the dispersion to be constantly high and higher than the velocity, or the velocity to be high here, higher than the dispersion. So we tried a new approach to solve this using a likelihood method, in which we have assumed that the distribution function of the line of sight velocity of the planetary is Gaussian. This is just a Gaussian. And the likelihood is the product of the probability for each planetary. So fitting this function, basically, and evaluating the maximum for the likelihood, we can find the best estimator for the rotation velocity and the dispersion. And here is the result, that as the square dots are what found in Noordermeer 2008. Sorry, the black square is what found in Noordermeer 2008, and the red and blue square are the same for the dispersion. You can clearly see here that that this angle approximation was imposed because this distance is constant, while the line is the value I found. And they are consistent with what we saw before, apart that sigma phi is higher than sigma r in the outer part of the region, and this is not possible. This would imply that the velocity increases with radius. An explanation for this is that what we are seeing is a contamination from bulge planetary to disk planetary. So if this red Gaussian describes the planetary as a disk, we have that the mean is the rotation velocity and the dispersion is sigma phi, while this blue Gaussian describes the disk PNE, but along the minor axis that has a mean of 0 and a dispersion of sigma r. If we add to this green Gaussian that could be the bulge contribution with 0 mean as well and sigma h dispersion, so dispersion in the bulge. On the minor axis, we still have a Gaussian, so it won't compromise too much what we find. Instead, on the major axis, we don't have a Gaussian anymore. So what we want to do is fit also this parameter, that's the dispersion in the bulge, and the fraction of planetary, and we want to give a probability to each planetary of belonging to the bulge or the disk. And to do that, we have used Galfit. Here you see a 2-mass image of 1023, and this is the model recovered by Galfit. And we fit a Debye profile for the bulge and an exponential profile for the disk. And with the output of Galfit, Galfit itself can build a model bulge and a model disk. And we use this to calculate B on T, so the ratio between the bulge light and the total light, that's sum of the disk and bulge light. And you can see it here. The bulge light is in black and the disk light is in white. And I don't know how well you can see it. But the red dots are the planetary nebula, and you can see that most of them are in the disk, but here we have also bulge light. So some of them belong to the bulge. And we estimate this value for each planetary, just basically counting the number of pixels in each position of the planetary. And so we can assign a probability of each planetary of belonging to the bulge and the disk. In addition, using a likelihood distribution allowed us, the likelihood is just the probability of each planetary of belonging to the model. So if we plot this in each bin, I'm doing a fit in 4 radial bin. So this is the central bin, this is the second set and last bin. And if we make an histogram in each bin of the likelihood of each planetary, we can perform a kind of sigma clipping, but the likelihood clipping. And here, with the yellow line, I show where we cut in this distribution, rejecting something like a 2.3 sigma outlier. And this is the result. So here I'm plotting, these are absorption light data from the Battista. And this is my fit, that in this case you can see the rotation velocity is flat. And this is the dispersion. Sigma r is the dispersion in the radial direction, and sigma phi is the dispersion on the major axis. You can see that now they are almost equal inside error bars. And this is the dispersion in the halo. That's also quite flat and is what we would expect for this kind of system, since is almost equal to the rotation velocity divided the square root of 2. We have quite big error bars because I'm fitting 4 parameters in each beam, so I'm fitting 4 parameters for 40 planetary. It's possible to decrease this error bar, imposing again the epicycle approximation, and so decreasing the number of 3 parameters from 4 to 3. Or, for example, fixing this value. But what I want to discuss now is are the rejections. So we have around 20 rejections on 183 planetary nebulae using that cut, the clipping that I showed before. And in this plot, I'm showing the position of the planetary nebulae with velocity corresponding to color. So the triangle are for the main galaxy planetary nebulae, and the square are from the companion galaxy. And so blue corresponds to velocity lower than 610, the systemic velocity of 1023. Then light blue correspond to a velocity between the systemic velocity of 1023 and the systemic velocity of the companion, and red is higher than 750. And here you can see the planetaries that are surrounded by a black circle are the rejected one, and you can see that most of them have a velocity that's consistent with the velocity of the companion galaxy. And also, they are like in the opposite side of the galaxy respect to the companion. You can see this better in this plot, where I'm plotting the radial velocity respect to major and minor axis. And the black line corresponds to the systemic velocity of the companion galaxy. The cross corresponds to the rejected planetary. And this, this empty circle, so the filled circle are planetary from 1023, while the not filled circle are from the companion. And you can see that somehow almost all the rejections are around the velocity of the companion galaxy. So, okay. And then I did a comparison between the planetary nebula data and the H1 data. I just overplotting them on the H1 image. The nice thing of this plot is that the blue square are the planetary that we associate with the companion galaxy, and they fell exactly in this H1 clump. And the rejected one, the scale coral is the same as before, and the rejected one are surrounded by this black square. So there is a kind of relationship with the H1 data, but obviously it's not certain. And then this is the last slide that I have, in which I'm showing what we obtain subtracting the galaxy model found with Galfit from a deep R-band image. This R-band image is the one used by Noordermeer to determine which planetary belongs to the companion. And you can see this is the companion galaxy. Once you subtract the model to the image, you can see the companion galaxy here, and you can see an excess of light here, that's exact opposite to the position of the companion galaxy in respect to the main galaxy. Okay, and I will conclude. So what I hope I explained is that planetary nebulae are excellent kinematic tracers, since they can be seen in the faint outer part of the galaxy, and this allowed us to or recover the galaxy past history, or determine, for example, the dark matter quantity of the galaxy, and that in the kinematic of the outer part of galaxy, the past history of the galaxy itself is somehow written, since it corresponds or to the galaxy formation period, or to a major disruptive event that the galaxy has had in its past life. That the likelihood method is a powerful method to estimate rotation velocity and dispersion, but anyway, the likelihood method has been used in a lot of different fields. And using this likelihood method with photometric information from a bulge-disc decomposition, we find a way to recover the galaxy kinematic. And finally, that 1023 has a kinematic that could be the one of a stripped spiral. That obviously complicated by a minor merger that this galaxy is ongoing, and so the outer part of the galaxy is perturbed by the little companion. And then in the last slide, I put a picture of, I went observing before coming here, and this is a picture of the control scheme in the William Herschel. That's it.
Okay. Any questions for Arianna?
So if I have understood well, so you're using a bulge-disc decomposition to have a probability distribution photometrical, and then you can associate to which component the planetary nebula.
Yes.
So, but you said that you have used the decumulative law for the bulge. Why don't you have used something more free?
We use a Sersic, and then we find that the n is almost 4. It's like 3.8. But then, okay, we wanted to see the color of the bulge and the disk of the galaxy, because it's possible that the planetary nebula in the disk and in the bulge, so the number that you expect change with color. So I, at the end, fixed the n to 4, because in this way, when I compare the Galfit model for different bands, so I did it in J, K, and R, it's like I know that I'm fitting the same model. But yeah, it's possible to let n free.
Can I make another question? What is your interpretation for the excess of light in the right side of the galaxy?
It could be associated with the companion galaxy.
But do you see any feature on the kinematics on the right side that you don't see on the left, for example?
Yes, yes. So using the planetary nebulae, what we see is that obviously, if our model is correct, we reject more planetary in the right part, and that planetary could be related to that excess of light, and could be kind of planetary that or are in a stream with the companion galaxy, or are just they belong to the companion galaxy and just now remain in the galaxy potential, and they're not bound to one of the two systems.
What is the fraction of the galaxy that is in the form of gas? You have been showing us H1 maps. And
respect to the total mass.
Yeah. These are gas-poor galaxies, right?
Well, it's one of the richest S0. Like, it's one of the S0 galaxies that is more gas-rich, because you would expect an S0 galaxy of not having too much gas, since in principle it doesn't have star formation. But this one is one of the richest S0, and especially the H1 distribution is really irregular. Normally, H1 is in a disk somewhere around the galaxy. but I don't know the question on that. Sorry.
Well, and do you have an idea of the age of the stellar population of this galaxy?
Well, in principle, it should be quite an older stellar population, like it should be a red, because it's a passive galaxy. But I don't know yet, like if there is a gradient in age between the disk and the bulge is what I would like to find in the future.
Well, I can tell you that the age gradient is not very strong. I know.
What, sorry?
From integral field from Saturn observations, we know that within one effective radii, it's not very strong age gradient. It's intermediate age, 5 to 8 years.
But, yeah, but we go quite further
Yes,
out.
yes. In fact, I have two small questions. And since you go that far, can you say anything about the dark matter content of the galaxy?
No, because I don't know. I don't do this kind of studies, but it will be possible. Like a lot of people from PNS does that, but I don't know.
And if you were to remove all the planetary that belong to the... if you were to remove all the planetary that belong to this infalling
Yes.
companion, did you see anything weird in the kinematic axis of the remaining planetary nebula, in the sense that do they align perfectly well with the photometric axis or with the main kinematic axis?
Okay. We haven't done this as well, but I think it's because it's assumed that the photometric axis is aligned with the kinematic axis. But then in the moment you divide between the bulge and the disk, you can see that the bulge and the disk axes are not aligned. So the PA of the disk is different from the PA of the bulge. So for sure in the
This is
moment...
on the planetary? Or photometric?
The photometric axes are different between bulge and disk. Probably you can even...
But this could be simply because the bulge is probably very round, and therefore defining a PA is difficult, right?
Yeah. So, well, you cannot really see it well here. But yeah, the out of Galfit gives you also the PA, and they are different.
And by how much? By 10 degrees or 20 or...
20. Yeah.
Any more questions?
Okay, just one. So you know that with the Grand Decan we have when it start working well, an instrument named Osiris, which have tunable filters. So do you think, it allows you to put the narrow filter on the wavelength you want and to move and scan the line. So do you think this can be of some use for you in this kind of studies?
Yeah, I think probably yes, but I don't know, like do you need to move the spectrograph or just to do a separator?
For instance, do you need something of high resolution, a spectrum of high resolution or do you simply need to locate where the line is? Imagine that you... So what is the resolution, the spectroscopic resolution do you need to do this kind of work? This is what resolution have the spectrum?
I don't even know. I think it can... Okay, so for resolution you mean the ratio between delta lambda?
I think you meant the spatial resolution or spectral? The spectral?
So we have... so we well, I don't know. Can be around 1,000, can be possible?
Is knowing exactly which ones of the sources that emit in O3 are planetary nebula. And that's the peculiarity of the spectrograph. The way it's built is done specifically to flush those points out. If you were to go to GTC with Osiris and just say, let's scan the O3 line, you will find the planetary, but there will be other sources of O3, and you won't be able to tell the difference between them. And that's the Well, she was saying herself there could be some Lyman alpha behind. There are other sources that emit in O3. There might be some diffuse O3 that comes from some other process. I don't know. The advantage of this, how do you call it? It's not cross disperse. It's counter
disperse.
Is that in that image you flag immediately. You can distinguish between planetary and any other source, and that's why it was built this way. So it's a nice idea, but in practice, well, for some targets I agree. The vast majority would probably be planetary nebula, I guess. But you won't be 100% sure.
Well, yeah, we could cross-check, like if you do it for galaxy for which we are a catalog.
But this will allow you to go much further. Our series will allow you to go much further, I think.
Yeah.
Yes. But this is done all in one shot. That's the advantage.
Yeah,
Agreed.
That would be good because we. And do you think you can observe also in the inner part of the galaxy? Because like planetary nebulae, with this instrument, we don't have information in the real center region where you have information with Sauron, because the light of the bulge completely, through the spectrograph, completely wash out the. So that's also something that would be good. Well,
Arianna, what's the field of view of the spectrograph?
it's 11 arcnewton. 11.
That's double Osiris. Depends on the resolution. Well, for the configuration I use is 5.6, so.
You can make a telescope.
Yes.
Okay, any more questions for Arianna? No. Well, let's thank her again.
Thank you.